I'm Fabrice, so a data scientist at Royal Mail. I've been there for a bit more than a year now. But before that, I spent most of my career in academia studying the formation of galaxies, trying to account for black holes, as you may have heard this week, and supernovae, into giant simulation, numerical simulations. So I did that in many different countries. But it's like everything else, like in life, when you get too much of a good thing, at some point you need a change. And because of that, I decided to go into business, in the business of delivering parcels. So that's what I've been doing since last year. Of course, I'm not alone in this endeavor, so I want to thank Loic, Dan, and Nick that have been helping me a lot with this project. So that was about me. Now the rest is about Royal Mail and data science. So this is the outline of my talk. I'm going to present you the team and what we do. Then I will make my case about what is important to look into route optimization in this business. And maybe we'll have a little example of how you run these problems. After that, I will describe the core of my talk will be on the science and the technology behind route optimization. And if we have time in the end, I will show you a little demonstration of the tool we built. Okay, so this is us at Royal Mail. 20+ people coming from 13 countries with a broad range of skills and background. Half of the team has a PhD, and people come from astronomy, obviously, but biology, chemistry, mathematics, engineering, computer science, obviously. We also work very closely with data analysts and data engineers in the department, and everything is sort of done in an agile way with end-to-end product delivery. So this is who we are, and this is what we do. So here is a range of problems we've been working on for the past few months. You might have heard about the estimated delivery window, which was launched last week, 10 days ago, I believe, where now customers receiving parcel can be warned the day before about a maximum of 4 hours window. So we in the team, some of us were involved into modeling and predicting that time window. And I believe that's a very nice service for all of us. Other problem we work on, obviously, fleet management. I don't know if you're aware, but Royal Mail has the largest fleet of vehicles in Europe. So as you can imagine, that requires a lot of management for the capacity, how you utilize it, but also the maintenance. We have a lot of trucks need to go to the shop. So we have project on optimizing the utilization of this fleet. Obviously, all we do is mail, so we need to forecast the expected traffic that we can see through our pipeline, and we do that using time series analysis. And like any other companies, there are frauds here and there, so some NLP and anomaly detection project. So all of these, as we all know, use the typical machine learning and data science toolbox with clustering and this type of technologies. What I'm going to tell you about today is more about combinatorial problem, optimization problem. So we will see how that is different from every of these kind of problem. Now, why route optimization? So as you know, Royal Mail delivers mostly letters, but with the rise of parcel delivery, Royal Mail is looking for ways to improve its service. To give you a few numbers about the market, the traffic last year was just below 2 billion parcels delivered in the whole country, and this is growing year in, year on. So surprisingly, more than half of this traffic was handled by Royal Mail. If you sum up all of the competition, this is still not as much as we do. So you can imagine the difficulty of setting a process to make that happen every day of the week, 6 days of the week, over almost 30 million addresses in houses in the country. So these are our constraints. We are also a company that is highly regulated by Ofcom. So we have rules to respect, targets to achieve, and this is not an easy market with a lot of competition. On top of this, with the growing traffic, expectations from our customers are growing. We need to provide a service that is very high quality. So for all of these reasons, the goal of looking into route optimization is to utilize the resources as efficiently as possible in order to account for the variation of demand that can be spatial variation or the daily variation in time or space. The requirement, obviously, as I just said, is to deliver a high quality service, but also rely on the current network we have, account for the fleet constraints and the workforce constraints in order to provide some tools that will help the postman and postwomen, the driver of these vans, deliver this service as quickly as possible. So to do this, route optimization needs to provide some recommendation in the way to sort parcel and the order how to deliver them. So this is what we are looking for with this project. Now, I hope everything is clear so far, what we are trying to do. To make it even clearer, I'd like to try a little game with you. I'm going to need 2 volunteers to run an experiment. Is there anyone that wants to play a little parcel delivery game, maybe? One here, thank you, please. Another one? You're welcome. So come join me on stage. I'm going to give you a bit of equipment. So we have Nick helping you with the postman vest. So what is your name? Daisy. Daisy. Thank you, Daisy, for joining us. So here is your bag. And your name is? So Vishnu. Vishnu and Daisy. Can we have a round of applause for Vishnu and Daisy, please? Thank you very much. So we try to set up a little problem where we are in code node in this control room, and there is a range of customers in the room, I believe. So if the customer could stand up, please. You have some letters in front of you, and show your addresses. So we have 10 parcels to be delivered today, from A to I believe, J? J, probably. So here are your parcels over there. So I'm going to give you, okay, one more thing, the rule of the game. So the 2 of you over there, we've got 10 customers to satisfy. I'm going to give you 1 minute to decide between the 2 of you how to sort these parcels, who is going to deliver where, and then another minute later to actually do the delivery. Just wait a little second. Now, your objective is to minimize the total time that it's going to take for the 2 of you to deliver these 10 parcels. I've got a couple of extra rules to give you. You're not allowed to run, because we don't want anyone to break a leg today. And very importantly, we have to deliver a high-quality service, as I said. So be nice to our customer. Ask how they are today, maybe something like this. Now, something different, but sometimes people are not home when you reach their place. So for this, we have little slip that you might know, you might have seen in your postbox. So if someone is not home, you will have to try to find a neighbor that will accept the parcel, and then go back to this person and leave a little slip to tell that the parcel is waiting at the neighbor. So I think you've got these 2, you've got some other there. Now, this is pretty much how the floor looks like. I mean, that's what we expect it to be. We've got our 10 customers here, the 2 of you. So if you're ready, I'm going to give you a countdown for sorting. Is this coming? I mean, that's up to them. Now, you've got 60 seconds to sort the job. I'll let you do that. Take your time, no rush. We want a high quality of service, so make sure you... So let's see how they do this. It's, I don't know if you realize, but that's something we do every day. So maybe not manually, but we have to decide who is going to go where. Oops, some parcel dropping, don't break it, you don't know what's inside. Okay, are you done? 30 seconds, so I'm going to ask you to stay there. Well done, very good job on the sorting. Let's see if that's a good sorting though. So another minute for delivery. Don't go too fast and be nice to your customers. Now is the time. Let's see. Oh, you've got a bag. Maybe you can put the parcel in your bag, you know? Okay. You're the postman. Aha, tricky, eh? Some streets are blocked, you see? Sometimes you have to go around like there is construction work on this street. Okay, so how is it going? We have someone going on the west of the town, the other one going on the east. Okay, are you here? No, he's not there. So you got your little sleep. Oh, I see some running over there. You're short on time. 10 seconds left. Are they gonna make it on time? 4, 3, 2, 1. That's it. So we've got one postie on time and someone that's taking his time. So you did a pretty good job. Can we have another round of applause for them? Maybe I'll get the mic now. So just to see how it went, can Nick tell us the result of what happened? So in what, who did what parcel in what order?
Sorry, can you say your name again, please?
Daisy.
So Daisy went to customer J, then B, then H, then G, then E. And sorry, was it Vishnu? And Vishnu went to customer F, then J, then C, and A, and D. But I think you were a bit unlucky and a couple of people weren't home, were they? Unfortunate for you.
And in total, I believe we had 1 minute for you and a bit more, so 2 minutes and a few seconds for the total of the delivery. Now, we try to make it as real as possible. So given that, that map, we actually found ourselves a little solution for you that would have been optimal and would have taken you only 68 seconds instead of 120. Actually, there is a row that we didn't know that you have space to go in between there, but the optimizer that we built, we run this problem into the optimizer, and the suggestion was to take care of these 2 people for the first postman, and the other would have gone through the whole way like this. That's what you did, like 11:15, pretty much right on, spot on. It is 11:15. That's what the software recommended for you. Thank you very much. So I think you deserve a little treat for this. You're part of the family. So here is a little, oh, it's broken. It's a little gift for you. Thank you for joining me on stage. You're welcome. So I hope now it's clear for everyone what we are trying to do. Now let's scale this up to a real Royal Mail problem. So in this mock example, I'm setting the problem to be tomorrow around Edinburgh. We have 50 parcels to deliver and an availability of 5 vans. Now, as you've seen before, we have time constraints. The delivery needs to happen within this window of 4 hours. It's within these 4 hours, the driver needs to start from the depot, deliver his load, and come back to the depot. So that's the main constraint. The definition of the problem is to visit every point only once, and minimize the time and total distance of the whole fleet, not only one. And so the question is how you get from here to there. That's what the recommendation looks like when you run the problem. As it happened, this problem can be solved with 4 vans only. So if you run your delivery service this way, you can do something in around 700 minutes and for 400 kilometers. that would be the most optimal way to deliver this service. Okay, clear for everyone? Now let's see how you build such a tool. So, as a good scientist, the first thing I did was to go to the literature. So this vehicle routing problem is actually quite a very old problem, but if it's easy to explain, as I believe I've done now, it's actually very difficult to solve. The combinatorial nature of this problem makes it NP-hard, and so given the number of points you have to solve for, the number of possible solutions, different solutions to that problem grow exponentially. Given my history in cosmology, I always like to give this number that if you have a problem with 60 points to solve, the number of combinations is more than the number of atoms in the universe. So obviously, we're not going to check all possible solutions. We have to find ways, methods to actually explore the space in a way that is that allows us to explore only interesting solutions, not all possible solutions. Just to mention that it's a generalization of the traveling salesman problem, which is kind of the same thing, but just with one van. Yeah, as I just said, we cannot, there are so many solutions for a given problem. We will never know what is, for big problem, it's difficult to know what is the best solution. So our goal is to reach near optimum solution. Nowadays, there are a lot of variants to the VRP problem, accounting for many different kind of constraints. And so if you look at the literature, there is kind of 4 stages when in the 60s and the 80s, people were looking to find exact solutions. So the problem was first described in this paper by Danzig and Ramser in 1959. And refined in this paper in 62, and for 20 years they were trying to solve small problems. Now, when they realized that there was no way to get anything for larger problem, from the 90s to the 2010 was the golden age of metaheuristics, so where you had impactful paper developing search algorithm to explore that space. So now it's trying to, it's not for exact solution, it's trying to find near optimal solutions. And then more recently, we've seen a surge of bio-inspired algorithms, which in a way are an extrapolation of these heuristics. But the good point about bio-inspired algorithm is that they parallelize very well, very easily. So for scaling up to large problem, it's very powerful. And very recently, for the past 3 years, maybe 3 to 4 years, we've seen attempts at solving this VRP problem with a deep learning network. Now, so these are the papers. So if you are interested, I can obviously send you these references. Now, because we are in a company that tries to solve real problem, when you want to develop a tool like this, you need something that works. So for this reason, we started from what is stable, what is well known. This field is, I believe, not quite stable, mature yet. So we looked at metaheuristics first. Now, to give you a view of how the problem looks like in a scientific way, not the problem I showed before, like I used a little smaller problem. This is a problem with 30 points, 30 deliveries, 29 deliveries, I believe. And so the way to view this problem is through graph theory, where you can think of all of these combination of possible solutions as a fully connected graph. And as I said before, you cannot go through every possible path in that graph. So the trick is to try to simplify the problem by using some clustering techniques, where you would account for the strength of the connection of the edges between nodes. As you see, the color here tries to show you how closely connected two nodes are. And then if you work on this simplified network graph, the game is to find what would be the best path, and this is an example of a suggested solution for this problem. Anyone can spot a depot here, the delivery hub. It's quite tricky to see in this visualization. Anyone wants to have a guess? So this is where you would start and do your whole tour and come back here. So one little tour and one big tour. So what I'm talking about heuristic, the method is about developing operators that will act on the nodes and on the edges. So the good thing about heuristics is that, at least for me, something that I like is you have to develop the methods yourself. Like there is no library ready to be used like that. So I quite like to have to do it myself. And as I said, this heuristic will allow you an oriented search through the solution space. So now I've been talking about optimization, and most of us work on optimizing some kind of function. In our context, our cost function will be defined by a combination of the total time of the delivery and the total distance with some weight, and then you can normalize by the parcel. So basically, these weights are defined by the business. What do you want to optimize? Is it the time only? You can have time only, distance, or a combination of both. And then I'm going to show you a little later how this works, but the whole point is to have this iterative procedure where you will try to minimize by stepwise this cost function. So this is what the optimization process looks like. Now, so this is the architecture we came up with to build that tool. So I'm going to walk slowly through this tool. We have a step of data gathering and acquisition here. And then the engine is run, soon to be run on the cloud. And at the end, when you produce your recommendation, you can provide an interface to give your recommendation. So acquisition first. As we've seen a little earlier, if you've got these addresses to be delivered to, like the parcels are here, you've got their coordinates here. So this is something you can query from internal database, like we know there are these parcels to be delivered. Now, the first thing you need to do when you've located your addresses is to build a travel matrix. And this is something we do by querying Google Maps. And so basically, the point is to have the distance and time to go from every point to every other point. So obviously, on the diagonal, there is no data. An interesting fact about this real-life problem is that, as you might have seen here, going from one point to the other doesn't always take the same time as going the other way around. So these matrices are asymmetric, and interestingly, most academias try to solve a simpler problem, and in general, they have symmetric matrices, so that makes our problem even more challenging, which is nice. So we've got our data. Hopefully, it's as close as the truth as possible. I mean, we rely on Google for this, to be honest. And so when we have gathered this, there is a step of initialization. So before we start optimizing, we need to set up the problem. So if you had something like this with a depot, 3 van, and something like 20 points, you need to start somewhere. Anyone wants to have a guess how to build a solution? Any idea? No? Okay, so the first one that comes to mind is the random one. Like most of the thing, noise is very useful to science in science, but not in this case. As you can see, assigning your points randomly to vans will give you a terrible solution, and then the optimization of this will be very difficult. So the next thing I did was actually to ask my daughter how she would look into this. And she said, "Daddy, why don't you just take a parcel and give it to the first van, and then the second parcel, you give it to the second van?" And so on and so forth. So she came up with this algorithm of sort to start from somewhere, and it performed quite well. There is another way to start this problem, is to assign some point, a fraction of the whole point, to one van, and then the closest point to the hub will go to the second van, and so on like that. This tends to provide little better solution, but it depends on your setup, on your problem. It's different every time. The last type of method we are using to initialize our problem is to use an assignment by postcode area. So some postcode area could be given to a given van, while the northeast will go to the second van. This is an initialization that looks a lot more like the business, what the business would do. Now, in terms of the problem, I've been telling you about the constraints before, that the delivery needs to happen in 4 hours for every van. Everyone needs to be back at the depot for every van. This is the only place when we don't enforce that constraint. When we start, we are not asking to be compliant to that constraint. And so basically, the way to choose between these 3 methods is to take the cheapest one in terms of the total it takes for to do the whole job. So we have a starting solution. Now we're gonna feed this to the engine. And so the method, the heuristic that I was telling you about, the most popular and powerful one is called a global search, a large neighborhood search, that apply 2 different operators to your graph, a destroy operator and a repair operator. So this pretty much looks like this. If you have a solution, an input solution that would connect every node in this particular way, the first operator is going to destroy partially this solution. So you need to give yourself a parameter, how much the fraction of destroy you want to use. So that's what it says there. So if I don't know if you can see, but some edges have been removed from the whole solution, which left you with a stash of points that are not in the solution anymore. So you reconstruct the partial solution with these edges and are left with a stash. And obviously, the second step, third step in this case, is to repair that route, that full route, by reconnecting those nodes to the rest of the solution. And this you do using a greedy heuristic, trying to reinsert them at a better place than they were before. And so, like this, you start from an input solution, and you build yourself another solution. This is what I meant before by I said exploring the space. The first solution was a solution to a problem. You end up with an output that is another solution to a problem. Now the question is it cheaper or is it not? Compared to if you look at the cost function we talked about before. And it's not always the case. Sometimes you repair a route, and because the way you repair it is not guaranteed, you will get always a better solution. So what people have done after this global search is to apply local searches around these newly found solutions, which are called k-opt. So k is for the number of edges you impact. So if you think of a simplified problem like this, when you just have a tour, starting at A, going to D, all the way to B, C, and back to the depot at A. A very simple mirror of the whole segment from D to B will actually give you a much cheaper solution. So it's a simple operator that applied locally and provide already a big improvement. So that's applying the operator on 2 edges, 2 opt. We built ourselves some other variation of these local searches. Here we've got 3 edges impacted. So some solution looking a little bit complicated like this. If you do a simple shift of the delivery C after D, you get a cheaper tour again. Last one, 4 opt. We've got 4 edges like this, looking a bit weird. And if you just swap C and B, one with the other, guess what? You get another cheaper tool like that. So all of these methods are available and applied at the back of the global search we did. And so this is, again, a new solution that you found. Sometimes these local searches don't find any improvement, so then you end up with what you started from. So this is still the engine. Now, at the end of every iteration of that process, we have to decide what to do with these solutions. And this is where the simulated annealing come into place, which is a well-known, quite old algorithm that allows you to get out of local optima during the convergence. So a little algorithm will look pretty much like this. So you start by what is the current best during your search. You need to know what you started from at that given iteration, what you ended up with in this iteration. There is a little update of a temperature parameter, but the point is, given the cost function that we described earlier, if the cost of this newly found solution is cheaper than the init one, you store both best and an input. Otherwise, you've got a given probability, which is an exponential decay here. That's a function of the temperature, to actually still accept this solution. So this newly found solution is not the best, but it's still good enough that you can accept it. And in this case, you update your input and return both best and input. When you do this, the whole point is throughout the convergence, for every iteration where you build, you destroy, you rebuild, it will allow you to get out of the local optima. Sometime at the end of a step, you end up at this point, you destroy it, you rebuild it, and you get, again, in the same local optima. So accepting a solution that is not better than the current one allows you to actually get out of it. So that's the whole point for the simulated annealing. After running this whole engine for many iterations, you've got a stop condition, you can find the best solutions you've explored so far. And you provide this to the user interface. So basically, the delivery to the business looks like this manifest. So you might have seen this one that was done for the problem we looked at together. So we have two levels of manifest. One is for the driver. Every driver is going to get the list and the order of the delivery he has to do. But the same data can be reshaped for a sorting manifest at the hub level when our parcel reach the delivery offices before the postman go on their delivery run to tell which parcel is assigned to which van and in what order it should be delivered. So it can help our postman to actually sort the parcel inside the van, put them first, put them last. All of this actually makes a huge difference when we go on the ground and do the delivery. Like there are minutes to be saved everywhere and kilometers as well. So that's the shape of our deliverable, and we have this interface for the manager to see how the recommendation can go. So if we have enough time, I think we do. 6 minutes? Okay, perfect. I will walk you through, not that. Okay. Can you see it? No, not yet. That's it. Okay, so this is our app where we pre-run a few. Where is my mouse? Can anyone see me? I mean, not me, but I'm lost. Where? Thank you. Sorry about that. Okay, so I've selected a sample of 4 delivery offices. I always like to start from the same example that we've seen before. So these are the 50 points with 5 parts, the 4 hours window. So if you try to run it with a number of van that is too small, the optimizer can tell you there is no valid solution to that problem. If you don't have enough resources, you will not be able to find a valid solution within the time window. So that's where you have the opportunity to update your resources and run again. And this is the solution I showed you earlier. So it looks like this on the map. You can have a look where to go. So everybody starts there at 3 o'clock in the afternoon, I believe. Now the fourth van is going to expect to drop his 10th parcel at that address in a given time. So you've got this information available here. Now, to give you a flavor of what happened in the background, this is the log of this little simulation. So this is the problem we are looking into, the address of this delivery office. Now, I mentioned to you the first stage, which is gathering the data. So we've loaded the postcode where we need to go. Then, I mean, all of that was done previously, but we queried the Google we queried Google Maps to access our traveling matrices. And then, initializing the solution, we had different possibilities: round robin, close, postcode area, sorted, and we find a initial solution here. So, as I said, usually you initialize it with a fair drop between the vans, and you've got this total time and distance. As I mentioned before, the solution doesn't have to be valid at that stage, but then you enter your convergence loop, where we're going to see some little information about, so let's go a bit down, further down. After 100 iterations, you started in that given step with an input solution that cost you 5.61, and then you find a solution that was cheaper than the one you started from, but not better than the current best. And so these are numbers about the number of valid solutions you had compared to the one you rejected. And at the end of this, you end up with a recommendation after 500 steps of this problem, taking that much time. This is the recommendation I'm showing you on the map. For us scientists, always try to understand what's happening behind the scenes. So this is the plot showing you the number of solutions explored as a function of the number of iterations. So all of the blue ones are the valid solution that we built for ourselves, and the red ones are the ones that actually we are breaking the time window constraints. Now in green, you have the solution that were reused by the simulated annealing algorithm, and in orange, it's when you reconstruct solution that you have already seen in the past. So if orange goes up too much, it means that you're not exploring anything new anymore. The way the convergence progress is like this. In blue, you've got the record of all the best solutions that you've explored so far. In orange, those are actually the cost of each solution that you've built for yourself. So as you can see, some solutions are cheap in cost, in total time and distance, but they are not valid. Sometimes the postman comes back too late. Even though it's a cheap one, we cannot accept this. And just to give a little flavor of the objective function, so for now it's just a two-dimensional function with time and distance, but you can imagine adding multiple sub-objectives to that function. And so that's how the space was explored. Just in the last minute, I'm just going to show you a couple more examples. So you've got simple problems, small problem in Cambridge. Now you can take some more complicated problem with 100 parcels. That takes a little longer to run on the laptop. But sometimes, as I said, you don't find a solution for this given constraint. So let's go a bit higher up, run it again. And funny enough, we found a solution with 5 vans, but we had to start with more to actually find this solution. If you start with 5, you don't always end up finding the solution with 5. Some other problem, we've got problem in, so that's Edinburgh, Swansea. Which one is this? So let's give it 5 vans again. And you find a nice butterfly like this, and you can change the weight, you can change everything, and it will tell you the recommendation. So I'm going to just go back to my slide to show you the conclusion. And if you have any question, that's still not it. No. And so in conclusion, that's the current investigation we are running, making sure we've got the right constraint from the front line. And we are looking into hard versus soft constraint, not always having sharp 4 hours constraint. And there is some ongoing work. So I'll thank you for your attention and happy to take any questions.
We've got time for just a couple. Do I see a hand here?
How do you deal with traffic jams? So the model seemed to be that the roadworks work, but day-to-day there's traffic jams, there are roadworks. How do you deal with that dynamically?
So currently the tool doesn't account for that, but you're right. This is part of the constraint we want to account for, live traffic conditions. So far, as I said before, we rely purely on the data we got from Google Maps. And when you do the query, it returns you 2 types of estimates, the best estimate and the worst case scenario when you have a high traffic condition. So we use this delta to account for the variation, but it's not fully, we don't do live traffic yet.
And one more question.
Thank you for the very interesting talk. And so, correct me if I'm wrong, you defined a cost function which is linear both in time and distance, and then you feed this into an exponential and compare the cost of the output with the initial solution, right?
That's correct, yes.
So there was a temperature defined in there. What does the temperature mean in this context?
So in this context of the converging process, the temperature allows you at the beginning of the search to accept solutions that are much worse than the current one. But as the convergence process goes, the temperature decreases. And when temperature decreases in the exponential, you only allow to accept solutions that are worse than the current one, but closer to the current one. So it kind of orients the search, allows you to get a terrible solution at the beginning and get better and better.
Okay, thank you. Unfortunately, that's all we have time for, but I'm sure more questions can come over lunch. So can we just, again, thank Fabrice in the traditional way?